Hello, everyone. Okay, so we are going to learn something called hypothesis testing today. Hypothesis testing is closely related to the. Is everyone able to hear me? I want to get a confirmation before I just give a lecture in silence here.
Yeah, we can hear you.
All right, great. Okay, so Zichu, I just wanted to touch base with you and find out, had I sent you some things about hypothesis testing examples to do as worksheets?
No.
No, okay, it's fine. I have a lot of them prepared, and we will go through and just do examples today with no actual worksheet credit. Hopefully that doesn't lead to an exodus of the class. This is useful stuff, and it's of course going to be on the last quiz. All right, so this stuff is really closely related to confidence intervals, and I want to make sure that everybody really appreciates, you know, when you say that you're doing hypothesis testing. Sorry, I'm going to close my door because the dog's carrying around his squeakies. All right, so hypothesis testing obviously is pretty central to the scientific method, right? I mean, when you guys were in maybe like the first grade and you had your first exposure to the ideas behind science, they probably told you that the essence of science is that you have a hypothesis and it's testable, and you go collect data and you confirm or reject that hypothesis. And this is how really in many ways science advances by not getting knocked down. And that's a sort of pauper viewpoint, but I think it's really the reality, right? You never really prove a theory. You develop evidence for it, and you develop evidence for it by repeatedly testing it. And as long as it doesn't fail the tests, the confidence in that theory gets stronger and stronger as time goes on. And eventually they become so strong that we decide that we can call it a law. And those are, of course, familiar things like F equals MA, which, even though we call them laws, do break down in cases where you leave the range of confidence in those things. Okay. So let me, with that out of the way, let me just say that the essential machinery for doing that hypothesis and test procedure is this procedure that Fisher came up with. So Ronald Fisher did a lot of stuff in statistics. And what we're going to do today is a couple of really silly examples to really ingrain this idea of how you test a hypothesis. All right, so we're going to just do this straight from examples. Okay, so Miss Keelis thinks that her milkshakes are better than yours. She asks all the boys in the yard to participate in a double-blind survey. Each boy tries the two milkshakes and votes on which one is best. All right, and then we have data. Okay, so there are a few things that I want to point out in this problem before we really get anywhere. One, there's a quantitative claim here, right? We can't do anything unless we make quantitative claims. So she claims her milkshakes are better than yours, and we have to come up with a way of an assessment, a sort of a quantitative measure for what we mean by better, right? So what does better mean? Well, she's gonna do better according to the results of a survey. If more people prefer her milkshakes than prefer yours, then her claim is true. All right. All right. So who is the pool? The boys in the yard, and each boy tries the two milkshakes and votes on which one is best. Okay. 12 out of the 16 boys prefer Miss Keelis's milkshakes. Okay. So let me label the elements here. There's a claim. And first, let me say that this whole thing is the claim. All right. And we're going to call that, at this stage, we don't know whether there's numerical support for that or not. Sorry, I've got this gigantic, let me change my, all right. Her milkshakes are better than yours. So this is the claim. Okay, and there's that's HA. Okay, we call it the alternative hypothesis, which might make no sense at this stage. Why do we have an alternative hypothesis and we haven't We haven't even talked about the basic one yet. This is the basic one, right? This is the one that, you know, if you're Miss Keyless, you're setting out to show that this is true. All right. Now, there's a key word in here, better, that has to do with quantities, and we have to be able to quantify that. Okay, so if we can't quantify the meaning of better, then there's nothing we can really do to settle this argument, right? So how is she going to do it? She's going to ask the boys in the yard to take a double-blind survey. Each one votes on which one is best. And now we have data. 12 out of 16 boys prefer Miss Keyless's milkshakes. So this is the data. All right. Now, right away, you can say that if you know, half of 16 is 8, right? So if 8 or fewer people prefer Miss Keyless's milkshakes, she has no basis for this claim, right? But there's also an issue where maybe 9 people prefer her milkshakes. And you might look at that and you say, well, that could just happen by random chance, right? And eventually, if 16 out of 16 people prefer Miss Keyless's milkshake, then you know that that wasn't just a random fluke, right? So this is the logic here is how do you use statistics to really place a degree of confidence on this claim? Okay, we want to place a degree of confidence on the validity of this claim. Okay, and that's what hypothesis testing allows you to do. It's a really powerful thing in experimentation, and particularly for those of you who want to go to the bio area. You know, the essence of biology is that all things are different, and so statistics end up being important because you have variability built in, according to Darwin, and that means that you don't always get these exact, precise, reproducible results, and you often resort to making a claim and testing it against a population. Okay, so it's you know, really an essential area in the bioengineering world to know these procedures. All right, so it's also important in a lot of other areas. Basically, anywhere that you have things that are really too complicated to make a precise, you know, first principles model of what's going on, you're probably going to need to rely on some statistics, and this is the language for doing that in most cases. All right, so we're going to use the data to test the hypothesis that the fraction of boys who prefer Miss Keyless's milkshake is larger than the fraction of boys who prefer yours. So notice here what we have reference to a population parameter P. Okay, this population parameter P is not the one in the sample. Okay, we took a small sample. This is our data. All right, and we can estimate what fraction in our small sample. You know, it would be 12 out of 16. So in our sample, according to our data, this would be 0.75, 12 out of 16. And this one, we don't know what it is, right? And this is why the procedure ends up looking a bit bizarre. The first time you see this, you probably think, why is everything all backwards, right? This is why we call the thing that we want to show the alternative hypothesis, because we don't know what the real population parameter is, right? It might be that 90% of people prefer Miss Keyless's milkshakes. It might be that 60% prefer her milkshakes. And those would lead to very different distributions from the data. The only thing we can really do is suppose that Miss Keyless is wrong, okay? So what we're going to do is suppose that she's wrong. That would mean that P is no better than 0.5. Okay, so we assume the best case scenario for her opponent's argument if Miss Keyless is wrong. And now suddenly we have the ability to use statistics to analyze these data. Okay, so let's see how this works. All right, so here's what we're going to do. So our strategy, we write down, always useful to write down the thing that you want to show. We want to show that this population parameter is greater than 0.5. For anything greater than 0.5, Miss Keyless is right. Okay? All right, now the null hypothesis follows directly from HA. So the null hypothesis is everything else. Okay? If the null is true, then Miss Keyless is wrong. All right? Do any of you guys know this song? I do this in class, and usually people are giggling and humming and stuff, and none of you know the song. Anybody?
I'm familiar with it.
Am I so old that the jokes don't work anymore? Okay. All right. Okay. Well, if you haven't ever heard the song, maybe you guys can go and listen to it, and you can hear things from back when I was young. All right. So the number of respondents who prefer Miss Keyless's milkshake is a binomial random variable. All right. Why is it binomial? Because it's a proportion, right? You're asking what fraction of people fit some category, right? And those are binomial distributions. So this is going to be different problem by problem. So recognize that that our estimate p hat is a binomial random variable. Okay. All right. So now what we're going to do is we're going to test Okay, so we take the best case scenario for the null vantage point, right? Which would be this case where we say that P naught, according to our null hypothesis, is actually equal to 0.5. Okay, so this is pretty forgiving, right? If you're her opponent, you say, no, I don't believe you. Let's suppose that they're equal and look at our data this way. All right. So now what we're going to do is we're gonna go through and estimate what we should have gotten. Okay. Okay. Now, because we know that binomial random variables, we know that there's a relationship between the mean and the standard deviation. Right? So notice that both of them just depend on this one parameter P. Okay, that means we're going to be able to use Z statistics. Same logic as for the confidence interval construction, right? So if you know there's a relationship between your two variables, you can go back to Z statistics. You are not using an extra degree of freedom to estimate the variance of this distribution. All right, so what is our test statistic? You can come in, but we're not ready for you yet. Okay, so the test statistic is going to be this value of Z that's going to be the data. Okay, so this is the number of people. If you want, this is in P hat. Okay, minus N times P naught. And we're going to divide that by the width of the distribution that we should have gotten if the null was true. Like this, okay? So what is this Z statistic? What is this thing we've just constructed? This is the standard deviation of that random variable for the number of respondents who would have randomly decided if it was 50-50, what is the standard deviation in the responses? This is the value that we got from the data minus the theoretical mean that we expected if the null was true, right? Notice that we compute the mean and the standard deviation in the denominator as though the null hypothesis was true. Okay, and the Z statistic now, let's draw a picture. So if the null was true, then what we've done is we've created this Z statistic that should have values scattered like this, okay? They should fall by construction around 0 if exactly, remember P naught was 1/2, okay? So n was 16. So if the null was exactly true, we expect about 8 people typically will prefer Miss Keelis's milkshakes. So the typical responses will be scattered in here, plus or minus 1 sigma from this thing. So I know that this is about -1 and this is about 1. And then we have these tails, right? And when we start getting data that lands way out here. In fact, if I compute the value of this thing, if I plug in all my numbers here, I use p naught equals 0.5, I use n equals 16, and that's enough. That's all I need to know. This ends up being 2, okay? So the data that we had was here. All right. All right, now we can look at this and say, if the data was anywhere over here, it's just completely off base for her to even make this claim. Okay, that wouldn't make any sense, right? The only data we have suggests that they're worse than yours, and so it's just nonsensical to even make the claim. Always want to do this check and make sure that the procedure doesn't make any sense if you don't have any supporting evidence. Okay, now the case that we're really interested in is where you do have some supporting evidence, but you're not sure how strong it is. Okay, so our data, the farther to the right we get, the more support the data gives to the claim that she's making. All right, so any data that lies here or to the right would be as strong a support for her claim or more, right? And now we can ask, what's the probability that I would have gotten this level of support or more by chance if the claim was false? Okay, you guys understand the logic? All right, so the p-value is the plausibility of the null hypothesis. Okay, and by plausibility, we mean in light of the data that we collected, how plausible is it that this was just a fluke? That this was just, that just happened to be that 12 out of 16 people liked her milkshakes, and so that's basically the idea here. Okay, all right. So we're quantifying when we compute. So this area out here, this is now this is the p-value. Okay, it's not always on the right. Okay, if she claimed that she was a better golfer than you, then we would be looking at the left end tail. All right, you guys see how the tail of interest depends on the nature of the claim. Sometimes the claim is just that they're different, and then we would count both tails. Okay, often in quantitative science, like you guys are most likely going to do, you have a definite inequality. One is greater than the other is the nature of the claim. But there are lots and lots of procedures for testing equality of the mean as well. Okay, so all right, so let's go ahead and finish this up. So what is that p-value? Well, now how do we get it? Somebody tell me how I get the p-value.
Would it be 1 minus the distribution to the left that we can get from our z tables?
Exactly. Okay, we get it from the z table. Exactly. So we want the probability that the standard normal variable is greater than this threshold value z naught. Okay, remember z naught, that happens to be 2 in this case. That's it's 1 minus everything to the left. Okay, so you guys can look these up however you like. At this point, you should be pretty good at using whatever table you're given. You can use the left hand. You could recognize that there's symmetry, and you could look up the left hand side, just swap that to a -2 and look up the left hand tail. Would be the same thing. Okay, the point is that you compute the area of that tail using the z tables, and you get 0.0228. All right, what does that number mean? Somebody tell me what that number means. We're almost ready for it.
Would it be the probability that her claim is false?
in a sense, it's the degree of confidence. So that number is the probability that the data that you got just happened by chance. Okay. And that the claim that she made was false, but the data you got, the evidence you got was just a fluke. All right. So so what this means, we say we are 98% confident. Okay, this was 0.002, oh sorry, 0.02. So we are 98% confident that H0 is false. All right, and by construction, if you're doing this correctly, then by construction, H0 is the opposite of HA. So therefore, we are 98% confident that her milkshakes are better than yours. All right, and that's the logic behind hypothesis testing. Okay, so this is you know, a rather confusing little procedure at times, but let me try to give a whimsical little thing to help you guys remember it. All right, so I'm going to completely humiliate myself as a professor here, but I have a helper. My daughter is going to help me with this. All right, Avon, are you ready?
Yes.
So so let's see. We want to is everybody seeing my screen here? Okay, are you ready?
Mm-hmm.
You start with the beat. Yo, I got a hunch, but is it really true? How can I convince a stubborn punk like you? Argue over lunch? No, that will never do. I need evidence, and logic will help too. Evidence will show, plausible or no. When the P is low, then the no must go. Fisher strategy, hypothesis and test. No ambiguity, this claim that I attest. Do the facts agree with what I have professed, or are the things I see just flukes made manifest? Evidence will show, plausible or no. When the P is low, then the no must go. If my claim ain't right, the opposite is true. Let's suppose I'm wrong. What should my data do? Analyze my data as though the null is true. How unlikely is it? That's the p-value. Evidence will show, plausible or no. When the p is low, then the null must go. Bid the null do, because the p was slight, and if the null is wrong, then my claim is right. Of course, it's not a proof, but for now, I've won this fight. Thank you, Avon. All right. Okay. Original lyrics. And if you guys memorize the song, you'll never forget the procedure. All right. So
Now I'm gonna go start my school.
thank you, Avon.
Bye.
All right. So now she can go and do real school. All right. So we just barely got that in under the deadline. So she has school in 5 minutes. All right. So we want to stop here and take a little 2-minute break, and we can reconvene at 11:30, and we'll do more examples of this procedure. Okay. By the way, the point of the rest of the examples is just to illustrate how you do it. So we just did one with a test on a proportion. These things all have tests, and the logic is the same in every case. The differences in procedures have to do with the assumptions that you make and the nature of the underlying distribution. Sometimes you don't know it, and then you're using the t statistics as your underlying distribution. Sometimes you know it, and then the procedure becomes very prescribed for the nature of your assumptions. All right, see you at 11:30. Okay, are we ready to dive back into this? So let's do an example where we're going to use Poisson statistics. Okay, we just did an example. Oh, sorry. Thank you. All right, so we're going to do Poisson statistics here. This is an example of hypothesis testing based on Poisson statistics, and we're gonna, you know, this is not going to be real data, okay? So, but this is the kind of thing that you might do if you're working in Professor Kong's laboratory, okay? So we have one cell that's exposed to a drug, okay? One cell is not. Okay, like any good scientist, we have a hypothesis and we have a controlled experiment where we might hope to establish some causal relationship here. All right, so the DNA in these two cells is then examined for mutations. All right, and you know, when you talk about mutations, if these cells survive the treatment, then the mutations must have been pretty low, right? So this is going to be rare events. Like if you think about all the base pairs, there are maybe billions of base pairs in the genetic code, and you're going to mutate a small handful of them. And so this is rare events, and then we can use Poisson statistics, right? Whenever you think of something that's a really small proportion or a small fraction or a small frequency, Poisson statistics become relevant for all of those things. Okay. All right. So the untreated cell. So we have data. The untreated cell incurred 3 mutations. Let's go ahead and just take our little graphic here and make a table. All right. So here is the number of mutations. And here's the condition. I made my table a little bit backwards. Okay. So the untreated cell, I just entered my data wrong. That would completely mess up everything, okay? Don't do that. All right, so the untreated cell incurred 3 mutations per 3,000. So it's 3 per 3,000 inspected bases, okay? So it's kind of like a survey again, right? We're taking a poll of 3,000 bases and checking to see which fraction of them have mutated. The treated cell incurred 9 mutations per 3,000 inspected bases. Okay, so Professor Kong wants to know whether he can claim that the drug increased the mutation rate, right? I mean, you can make this claim, you can eyeball it, you can hope for the best, but if it's 5 versus 3, you might say that might have just, if I did it again, I might not get a result that confirms my opinion, right? So what we want to do is to place a degree of confidence on the claim, right? So let's systematize this. Okay, so Professor Kong wants to assess confidence in the claim that the drug increased the mutation rate. All right, so this is the claim. The drug increased the mutation rate. So this thing immediately becomes my HA. Now, in order to make any sense of this, I have to come up with some way of quantifying this, okay? So, you know, we know that these mutations are rare in both cases. And so we're going to think of the two populations as having Poisson parameters, okay? So we're going to define a lambda1 to be the mean number of mutations without the drug, okay? And lambda2 is going to be the mean number of mutations when we do have the drug, right? Now, these are not, let me emphasize this point again, this is not equal to 9 over 3,000. Oh, sorry, I'm flipping them around again. This is not equal to 3 over 3,000. And this is not equal to 9 over 3,000. Okay, the population has some mean, and these were the samples. This is the data from your sample. It is not the population parameters, right? So the claim that we make is about the broader population, and the data that we have is about this 3,000 base pair example sample. All right. So HA is the claim that the drug. Now we can basically say that HA is the claim that the drug increases the value of lambda. All right. And because of that, then what would be the null hypothesis? What is the null then?
That the drug does not increase lambda.
Great, great. Okay, the drug does not increase lambda. So let's go ahead and try and write that down in a quantitative statement. Let's look at the two lambdas. I'll write down what you said here. The drug does, H0 is that the drug does not increase lambda. So what would that mean about my lambda 1 and lambda 2?
That they're equal.
Oh, that's the case I'm gonna use in my math. Okay, it's the best case scenario for our opponent. Okay, but what we really write down for our null is that lambda 2 should be no greater than lambda 1, right? They could be equal, and that's the case that we're going to actually do the math for. Remember, we do this with the best case scenario. I think I just got a little temporary Zoom bomber. I'm glad he's gone. Okay. Great. All right. All right. So what we're going to do now is let X be. So we're gonna give these things names. I'm gonna move my table over here again. Okay, so let's call this column. I'm struggling here to lay this out on the fly. We're gonna give this a name. Okay, so this is going to be X2, and this is going to be X1, okay? And it's just X2 equals 9, and X1 equals 3. You could formulate all of this with fractions, but you would have to go through and use those variance identities. Take the Poisson distribution and variance formulas, that's still the underlying distribution, but divide by the size of your sample. And then in the variance formula, that size of the sample gets squared. And then you can do it all that way. And if you want, we can go through the other language for doing the same problem in office hours. Okay. All right. So this is now getting to a point where we can begin to say some things. So now what we do, because we're assuming that we have, so let's do part, so this is part A. If we had a worksheet, this would be what we were doing in part A, is just defining variables. Okay. Essential step. Okay. This is step 1 in every problem. I want to go through and write down, some variable names for your data, your null hypothesis, your alternative hypothesis, any parameters from the underlying distribution that you know, and parameters that you're going to be assuming. Okay. Now, in the next step, what we're going to do is begin to apply the assumptions. Okay, according to our null hypothesis. Okay, so let me write that down. Apply assumptions according to the null. Okay, remember the lyrics of the song. Okay, the lyrics of the song say, let's suppose I'm wrong. What should my data do? analyze my data as though the null is true. Okay, so this is what we're doing. We're going to apply all of the assumptions to our data and the results as though our null hypothesis was true. And we're always using this best case scenario for the null hypothesis. So we make a pooled estimate. What do we mean by a pooled estimate? If there's no difference, so if lambda 2 equals lambda 1, okay? So we're assuming that lambda 2 is equal to lambda 1, okay? This is our operational assumption. I'm trying to write that for our analysis. Okay, and it is the best case scenario for our null hypothesis. Okay, so we make if this is true, then these two populations that our data came from are exactly the same. And if you knew that that was true, what you would do if somebody asked you to estimate lambda is to add the number of mutations that you got in experiment 1 to the number of mutations that you got in experiment 2, because theoretically they should be the same according to the null, and take the total number of trials that you did, which is just 3,000 over 3,000, and this comes out to be well, let's go ahead and so it's the mean number of mutations without the drug. So we're going to multiply this by 3,000 again. Okay, so this is the mean number of mutations in an experiment with 3,000 trials would have ended up being 6. Okay, so this is a pooled estimate based on 2 experiments for the mean number of mutations in an experiment with 3,000 trials. Okay, you guys see how this works. It's really important to go through and do this stuff systematically, construct these things. At this point, we're using all the probability that we learned, all the statistics that we've learned, and it all comes together in this part of the course. And you really have to think very carefully about how to construct these parameters. Okay, so this is our pooled estimate for the lambda parameter, the common lambda parameter. All right, so this is the answer to part B. Part B literally says obtain a pooled estimate of the lambda parameter. Okay, so I wrote that in more general parlance. Apply assumptions and estimate parameters according to the null. Okay, according to the null, the two populations are the same, and so this is our pooled parameter. You guys have any questions? Go ahead and stop me if you want to ask why we're doing the things that we're doing. All right. Now, according to the null hypothesis, what are the mean and the variance of the random variable? So notice the logic here over and over again. According to the null, what are let me go ahead and just write them in symbols. Okay. What are the mean and variance? I wrote the standard deviation, but you guys now at this point in the class know that I can get one from the other. Okay. All right. Notice that what I'm looking for are the mean of the difference of x1 and x2 and the standard deviation in x1 and x2. Okay. So if we really had 2 equal populations, if x1 really came from the same population as x2, what would be the mean of the random variable x1 minus x2?
For a Poisson distribution, would the mean be our pooled estimate?
Okay, so the mean of the mean of x1 itself if they were really from the exact same population, would be lambda, whatever the real value of lambda is, and we don't know it, okay? But I'm asking, what is the mean of this variable if x1 and x2, according to the null, really were random variables drawn from the same population? Doesn't matter what kind of statistic is it, right? It's 0. Now this one is not 0. So this one is 0 for all distributions. This one depends on the situation. Okay, in this case, we're going to be using Poisson statistics, and maybe that's where you were going, is to use Poisson statistics to estimate this sigma. We will do that in a moment. But this one, it's important to recognize, is just 0 by construction, right? All right, so according to H0, we have that mu x1 minus x2 is always going to be 0. Okay, and what about this guy? So I've already told you that we're going to use Poisson statistics here because we don't know the values of lambda, but we know that they're approximately given by the Poisson parameters that we just estimated. Okay, so this is going to be, first let's use our variance identities. So this is going to be x1 squared, the variance of x1 plus the variance of x2. You guys remember this formula, right? That minus sign makes no difference in the variance formula. So it's just the variance of the two random variables in the linear combination. And this is going to be, now this is the answer that you just gave me. What was the variance of a Poisson distribution?
It would be the same as its mu value.
Exactly. Okay, so this is something that and we don't know the real lambda, but we're going to say it's approximately given by the lambda in each case. There are two of them, right? So this is 2 lambda hat, and we don't know that parameter, but that's okay, because what we're doing is constructing a procedure to place confidence intervals on its value, basically. All right. So now that part is done. I'm unable to scroll up and down here. Okay, let's do part D. So we're going to execute the following hypothesis test. We're going to execute our hypothesis test here using answers from parts A through C, okay? Okay, and there's a hint here on the worksheet. I will put this worksheet up on the web. We're going to need to justify the use of Gaussian statistics. Okay, you can see I was really feeling very generous here. I might ask you guys to just know to use Gaussian statistics, but I seem to have made this one a little bit easier. Okay, so the key thing here, why can we use Gaussian statistics for this problem?
Is it because of the high number of data points?
That's interesting. Okay, so how many data points do we have? We looked at a big, long, open reading frame on the DNA, and we looked at 3,000 base pairs. Do we have a lot of data? In a way, do we have a lot of data has to do, if we had 1,000 mutations in that 3,000 open reading frame window, we would say that's a lot of data, right? But when we only have 3, now the events are so rare, the same open reading frame gave us very little signal. And because it's small number statistics now, we would say that the events are rare. And so the data set really isn't very big to say that 3 is a precise number, right? I think that, yes.
Oh, in that case, then, so when we take a reading, but then don't have a signal, we don't count those as part of our overall data set?
This is a really delicate point here. So the random variable that we're looking at is x1 and x2, and we're trying to make a assessment of the fraction of the number of these mutations that we expect. You know, it's true that we took 3,000, we queried 3,000 base pairs, but we only saw outcomes of 3 and 9. And so, so 3,000 base pairs might be a perfectly good, huge sample size for looking at certain things. What fraction of them are adenosines, for example, right? If I want to know what fraction of the base pairs are adenosines, then 3, as opposed to guanine and cytosine and tyrosine. So that's a huge data set for that number, because the number that you're estimating is 25% of the sample size, approximately. But when you're estimating something that's really small, you're going to need more data in order to get an accurate estimate. This is maybe something I didn't emphasize enough when we talked about sample sizes. But remember that when we said that 5 or greater is a good sample, we were looking at things where each member of the sample has some characteristic, and you're estimating the average of that characteristic. Here, you're counting the number of errors, and it's not clear how you frame that in terms of a estimation of the mean kind of thing. I hope maybe I'll have to think about this and try and give a better answer for when you do one or the other. Yeah, I'm gonna have to come back to that on Thursday. Okay, so it's a good question. So the key thing though is that because these are extremely rare successes, we're going to need more data to accurately estimate their frequency. All right, so now we're going to justify the use of Gaussian statistics here. So basically this is because we know the underlying distribution. Okay, technically it's binomial, but it's binomial with an extremely small p, and in the limit of small p, binomials become Poissons. So we are taking that shortcut that the Poisson distribution is a lot easier to work with than the binomial. And so this is the justification. Okay, Poisson, as long as I'm far from the edges of the interval, can be thought of and modeled as a Gaussian. All right, so let's go ahead and do a little picture here. So here's our random variable x, could be x1, x2, doesn't matter. In the null hypothesis, we're assuming that they're the same. Okay, so it looks about like this. And, you know, really that's a discrete distribution. All right, and somewhere in here is 6, and this is 0. And there's some probability, if I make a Gaussian model of this distribution, there's a little probability that I have a tail that extends to the left. So we're not completely safe with this assumption. And that's, you know, notice how I'm using the value of x instead of the 3,000, right? So this gets back to this point, are we estimating a average property among the 3,000, or are we estimating the number of the 3,000 that have some characteristic or don't? All right, so so this is the little approximation that we're making, and we're going to assume that we're okay with that tail. Okay. So that's an approximation. We want to be aware of how much error it's going to cause us, and it's going to be pretty small in this case. All right, so now we have 2 Poisson distributions with lambda equals 6, and because there are 2 of them, so why are there 2? Because x1 was Poisson and x2 was Poisson, and we're adding those 2 random variables together, and so that's going to be in a sense, even better. All right, so this is going to give us our Z statistic is going to look like this: x2 minus x1, okay, minus the theoretical value. So this is mu. I'll write mu2 minus mu1, but that's mu x2 minus mu x1 according to our null hypothesis. And we divide this thing by the standard deviation for this random variable. Notice where, if this is the random variable in the numerator, it's the standard deviation of that random variable that goes into the basement. Okay, so that's the value of my Z statistic. I can now plug in the numbers here. X2 minus X1 was 9 minus 3 is 6 upstairs. And downstairs, we had a, this was going to be 6. And this is 6, okay? So sigma X1 minus X2 is 12. And I can now compute some values for this. So if I plug everything into my calculator, I get 1.732. Okay, so now let's do our calculation. So remember, always nice to draw this picture. I think helps sort out your thoughts. All right, so we found. So if the null was true and the drug had no effect on the mutation rate, I expect data scattered around here, right? And typically it'll fall plus or minus 1 standard deviation or so. So there's -1 and there's 1. All right. You know, the way we've set it up, X2 was with the drug, 1 was without. So we expect any drug that's actually having an effect will actually move the results over here. Indeed, my data is right here, okay, at 1.732, okay? And this is my p-value, okay? Somebody tell me, what is that p-value? What's our p-value?
Is that the probability that the drug does increase the mean value of mutations?
Okay, I was expecting a numerical answer, but this is a good point. You're asking a good question here. The p-value is not the probability that the drug increases the mutation rate. The p-value, remember what we're doing, we're assuming for the moment, we're playing devil's advocate with ourselves, basically. We're assuming for the moment that the drug does not increase the mutation rate. And then we're asking, if that was true, the drug has no effect, then what's the probability I would see data that was like mine or more supportive of my alternative hypothesis by chance? Okay, so that's the reason that like mine or more supportive is the reason that it's a tail, everything to the right. Okay. So the p-value is this number. It's plausibility. Okay. So plausibility of the null in light of the evidence. Okay. The plausibility of the null hypothesis that there's no effect of the drug is this small probability that I would have gotten data like mine or more supportive of the alternative hypothesis if the drug had no effect. Okay. And that in this case, the numerical value, anybody look it up? Okay, you guys want to be fast at doing this. If you're passively sitting and watching, that's fine. But I hope you guys are studying outside of class then, because you have to learn how to use these tables and compute these z values. All right, so the p-value in this case ends up being 0.0418. What does it mean? What does that p-value mean? Very important that you guys learn how to say this correctly, because the real lawsuits are made of this stuff, and challenges to scientific papers and all kinds of things. All right, so to a precise statement of what this means is that we are 90. So now we take 1 minus this, 95.8% confident that the drug increases. I don't know why it does this sometimes. It stops writing. Mutations. All right. So this is what we can say based on the evidence that we have. We're 95.8% confident that the drug increases mutations. Okay. So rule of thumb in statistics, in absence of any risk analysis or anything, 95% is a pretty accepted confidence interval that would allow you to publish or make a claim in the literature or in a documentation for the product that you're making. But you do have to be careful, right? So if mutations are something extremely dangerous, you better be more than 95% sure, right? So this is these things always, this is what we can say. What does it mean, and what action will you take based on it? Depends on the context and the probability that you get it wrong, right? So suppose, for example, that you're testing a chemotherapy drug, and you say there's your data shows that there's a 90% chance that the drug is effective. Well, if people are taking that drug, they're probably not going to take another one. And there's a 10% chance then that the drug isn't doing anything. And so you probably want to have more confidence than that before passing the clinical trial on that drug. Okay, so all of this goes into false positives and false negatives, right? So 95.8% is the confidence that the alternative hypothesis was true, but that means that there is a 4.2% chance that the alternative hypothesis was false, and your data just was a fluke and it appeared to support the alternative hypothesis. Okay, and this is why in science it's very rare that we can say that we have a proof for anything. Usually we have data that supports an assertion or a hypothesis, but we can never be completely 100% sure. And of course, you guys all know the long history of corporate manipulation of doubt and talking about, the science isn't settled yet. We don't need to take action on this expensive legislation because we haven't really completely proved that whatever, insert your political debate. Vaccines cause autism, humans cause global warming, all of these things, right? There are always degrees of confidence associated with these things. And the fact that a good scientist is out there talking about confidence intervals instead of absolute 100% certain proof, which they shouldn't be, gets abused by people who want to exploit that doubt to say the science isn't settled. Anyway, I will not go farther into these debates, but it's sometimes frustrating to hear the news and the misconstrual of the nature of the scientific process for as an excuse for inaction. Okay. So what do we want to do now? Maybe we have time to go through one more. But before we launch into one more, let me say that I will put a whole bunch of examples of these things on the web, and you guys can go through and practice the procedure. We will probably go ahead and start regression analysis on Thursday. And so we'll just get as far as we can with doing these things today. All right, so let's do this example here. Okay, so we have a let me share this example. Stop share. New share. Okay, in this example, we have a group of students that goes out to celebrate after finals, and they are feeling nostalgic for their statistics class, which in the future should be named 411. Okay, you guys took it as 494, but the plan is to make this statistics chemical engineering 411. They invent a human balance bar game. Okay, player A pours an amount V1 of liquid into glass 1 and an amount V2 of liquid into glass 2. Player B puts on a blindfold, and then the two players execute the following procedure 12 times. Player A puts the two glasses randomly into the two hands of player B, and player B decides which glass contains more liquid only by lifting them. If player B can confidently identify the larger drink, he wins it. Otherwise, B gets the smaller drink. When player B removes his blindfold, he sees the following data. Glass 1, 4 wins. Okay. Glass 2 has 7 wins. Okay, this means that player B picked glass 1 4 times and player B picked glass 2 8 times. Okay, so they don't just get one try at this. They get to weigh them multiple times, and it's a made-up game. All right, so my games, it's pretty hard to decide who's the winner. All right, so player B picked glass 1 4 times, and player B picked glass 2 8 times. Okay, so let's suppose that V2, that's the amount in glass 2, was indeed greater than V1. Okay, but now what we want to know is player B really detecting the difference, or is this random fluctuations? Okay, so player B claims that he's won, and player A claims, well, 8 out of 12 is just luck. Okay, how confidently can B claim that he really can tell the difference? Okay, so the null hypothesis, let's see, what would you guys think we should set up as a null hypothesis for this problem? Here, let me take away the answer. All right. Okay, somebody tell me what would we do for a null hypothesis here? Oh, I just stopped the sharing. I didn't mean to do that. All right, it's back to sharing. What is it going to be our null hypothesis?
The null hypothesis would be the player's inability to distinguish the two classes.
Yes, and the key thing is that we have to think about whose claim are we testing, right? How confidently can B claim that he can really tell the difference? So B wants to claim, I can really tell which glass is heavier. And he has to now play devil's advocate for himself. In order to quantify confidence on that claim, he has to be his own devil's advocate here and construct a null hypothesis that would agree with A. Okay, and so that null hypothesis is that B cannot really tell, and that B is just guessing with a 50-50 chance or worse at getting the right answer. So our null hypothesis is that the fraction of times that he gets it right is less than or equal to 0.5. And if P is equal to 0.5 with N equals 12 trials, we can go through and we can begin to construct our testing statistics. So our mean of the number of times that he's going to get this right is going to be 6. Okay? If the null hypothesis is 50-50, or sorry, if the null hypothesis is correct, then his guesses are 50-50. He guessed 12 times. He would expect that to come up 6 times that he got it right. How many times, what is the standard deviation in the number of times that he would get this right? It's that variance formula for a binomial distribution. So that's going to be n times p times 1 minus p. In this case, that comes out to be the square root of 3. All right. And now what we're going to do, so now notice what we did. This is all according to the null here. I don't know what to do to highlight this, but my cursor is right here over these things. I hope you guys can see it. So these things are, according to the null hypothesis, these are the mean and the standard deviation that we should have seen for the real underlying distribution. The null hypothesis specifies the underlying distribution. Okay. And now we compare that to the data by using Gaussian statistics. Sometimes we'll use T statistics. Okay. So Z is going to be equal to the data that I got minus the mean that I would have expected if the null was true, divided by the standard deviation that I would get if the null was true. And that's 1.155. Okay. So this is pretty weak evidence. B is in trouble here, right? So there's some evidence. He could claim maybe that he's able to tell the difference, but also A could claim you can't tell the difference very well, and we're not really sure if you can tell the difference at all yet, right? So how do we quantify that? The p-value here is going to be the probability that Z is greater than 1.155, and that's only 0.132. So we are only 87% confident, based on the data from this game, that player B can actually tell the difference between the volumes by weighing them. Okay. All right. So so the little example here goes on. They agree that B should identify the larger drink with a 90% confidence threshold to win. Okay. So now we begin to talk about confidence thresholds. Okay. And I apologize for this. I don't know why these things even exist, but they are everywhere in the literature and you can't avoid them. Okay. So I taught you all of this stuff from a confidence, degree of confidence, plausibility, p-value standpoint. And in principle, I think that's all you should really ever need, is to state your p-value and draw a conclusion in a case-by-case basis. But in the literature, there are these somewhat ad hoc rules of thumb that say suddenly evidence becomes significant when it reaches a 90% threshold. Or in other fields, they might say somehow the evidence becomes significant, goes from insignificant to suddenly significant when it reaches a 95% threshold. The reality, as I see it, is that the evidence is a continual scale, and it's getting stronger and stronger as the p-value decreases and as the degree of confidence increases. But people talk about these threshold significance levels, and they call that alpha. Okay. So if we establish a rule that we want a 90% confidence threshold, then the alpha parameter is 0.1. Okay. And this basically is just a cutoff for where you can draw the conclusion that your result is meaningful and where it is not. So when the difference between drinks is very large, B can detect the difference, right? So if I take a 2 pint glasses and I pour one of them full and one of them completely empty, then probably the data will end up being really skewed towards 16 out of 16 times or 12 out of 12 times player B was able to tell the difference. Okay. When I make them 160% full and 150% full, now it's really hard to tell the difference, and my data will look like the case that we did in the example, maybe only an 87% confidence that B can tell the difference. Okay. So what I wanted to illustrate here is this idea that that you have type 1 errors. Okay. So a type 1 error, sorry, I think I need to, all right. So type 1 errors have to do with the I have to recap this myself. I'm confused. Zichu, do you remember which one was type 1 and which one was type 2? All right, we're gonna have to come back to this.
No,
I don't
think so.
Okay, we will recap this on Thursday. We're out of time now anyway. So I'm saved by the bell on my lapse of remembering which one was type 2 and type 1. Okay, but you can see here that there are 2 different ways that we can get things wrong, right? So one is that the null hypothesis is true. He has no ability to tell, but the data shows evidence that he can. Okay, and that's this 1 minus your p-value, which is the and I don't know which kind of error they called that. I'm sorry. And then the other case is that they can that he really can tell, but the data set would suggest that he can't. Okay, so there are two ways that you can have reach the wrong conclusion in these tests. And the one thing that's important about this alpha value is that it does have to do with your propensity to reach these wrong conclusions. So we'll come back to this on Thursday. It's a fun topic. I like this stuff, and I will see you guys again on Thursday.
Oh, get your sandwich then.
Oh no, you're on the recording.